my name is Alessandro Bossi. I will now present the problem coming in this section. The problem number is linear and you can calculate yourself. So, the problem says that if you project in real time what a camera is recording, you will see that you have nested images in the screen. This effect is known as the Droste effect. The problem has to calculate the speed of light considering the delay of the electronics and the delay due to the speed of light. And as under what condition can this effect be used to determine the speed of light. On the left side we will have the reason why we have this effect known as the Droste effect. This effect is known as Droste effect because there is a mark of cocoa that is called Droste, and is not a physical effect, it is an effect known in art. The second image is we had a selection for the model, and we have the honor to have the model here in this room. And as you can see, there is like 3 or 4 images inside the screen in the picture. So we will divide our problem in 5 steps. The first one, we will show our approach to the problem. For a normal screen like this screen and this camera, we will have a frame per second of around 60 frames per second. And in this period, the period is like 0.02 seconds. And in this time, the light will travel nearly 5,000 kilometers. Therefore, we will need like a screen in Lausanne or Milan and the other camera in New York. Therefore, it is a bit unpractical in a lab. And moreover, we will need like a huge screen and camera. Therefore, we had to think in another way. We notice that every point on the screen corresponds to a point in the camera. That this point on the camera will be activated, that in turn will activate a point on the camera, on the screen, that in turn will activate a point on the camera, and so on. Therefore, we will have a series of laser photodiode. And we notice that laser and photodiodes are orders of magnitude faster than screens and cameras. But we notice also that it is not an infinite repetition of images. That is because there is a discretization of pixels in the screen. And in order to have a changing signal we will turn off the first laser when we reach the last photodiode. And we will measure the frequency between we will measure the frequency of changing. The frequency will be given by 1 over the delay due to the electronics plus the delay to the speed of light. And changing the length between the lasers and photodiodes, we will try to measure the speed of light. So, the setup, we build a circuit that will have a laser that is always on. This laser will shine its light on the photodiode, and this photodiode will in turn activate another laser that will shine its light on the photodiode that will turn off the first laser. And therefore, we will have a changing signal throughout our experiment. And this is an actual picture of the setup. We notice 3 main elements that we did not discuss before. The first one is the optical fiber. It is, the reason it is that we wanted to change the distance without using mirrors and having a long distance for our length. And the optical fiber were the best solution to our problem. The second one is the Arduino Uno board, and it is useful to use the Arduino Uno board because it has a sampling frequency of 10 megahertz, and it is way above what we needed. And the third element is that we used a roll tape scotch to isolate the Arduino Uno board to the optical table. That's because the optical table was a conductor of the electricity, and it risks to fry our Arduino board. So now the experimental results. we firstly measure the speed of light, the delay, of the electronics by putting the lasers on top of the photodiodes. We found a frequency of 107 plus or minus 1 kHz and the corresponding delay of the two electronics of 9.3 plus or minus 0.1 microseconds. And looking at datasheets, we can say that it is a correct measurement for only the electronics. And we can say that in 100 nanoseconds, light, as we know, travels like around 30 meters, and this will be the minimum distance to measure the speed of light. And it is reasonable to measure with a fiber optic cable. But if our objective was to decorate the laboratory, we absolutely reached this objective. That's because we have a beautiful fiber optic that scattered a little bit too much light. In fact, we wanted a fiber optic that the input laser was the same as the output laser and not maybe a tenth of the original intensity. That's because you can see that there are a lot of scattering center. And the photodiode was not enough to, the intensity was not enough to activate the photodiode to be able to, for an Arduino, to read the signal, because the voltage we had was too low. Now, what have we to do to improve the experiment? Firstly, we obviously have to buy a better fiber optic cable. Secondly, we could amplify our signal before measuring it. That's because, as we said, the intensity, the voltage, was not high enough. Thirdly, we could use an oscilloscope to directly measure the period, ignoring the amplitude of the signal. And fourthly, we could absolutely change our circuit and redo it from scratch with a higher reverse bias on the photodiode and using some MOSFET instead of BH80. That's because with these two, they are faster and have a higher sensitivity. Finally, the conclusion. In this presentation, we have explained our approach to the problem. We have explained how we wanted to measure the speed of light with this method, and then we presented the circuit we built. We showed the setup works, but due to the low quality of the fiber optic cable we used, it was not possible to perform the measurement. And then finally we explained how we wanted to improve the experiment to actually have a measurement. And to conclude, the problem asked under what condition can this effect be used to measure the speed of light. There are three basic requirements. Have a short delay of the electronics, have a delay of the speed of light comparable at least to the error of the measurement for the electronic signal, but also we need a signal. Thank you for the attention.